Hey guys, today I would like to tell you about an algorithm that helps us to detect if a graph is a planar one or not. Let me give you a few definitions first. A connected graph is a graph in which you can find a path between any pair of vertices. This graph is a connected one because you can find a path between any pair of vertices. Let's say if we take these two vertices, we can find this path, or this path. This graph is a tree, as you can see, and it is also a connected graph because you can find a path between any pair. Let's say if we have this and this vertices, we can find this path. This graph is not a connected one because we cannot find a path between this and these vertices. The second definition. Biconnected graph. Biconnected graph is a connected graph where you can remove any vertex with its edges, and it is still gonna be connected. This is a biconnected graph because if you remove any vertex with its edges, it is still gonna be a connected one. This is the example of not biconnected graph. This graph is connected but not biconnected. Let's say we remove this vertex with its edges. As you can see, now it's not a connected graph anymore. And the third definition is bipartite graph. Bipartite graph is a graph where you can split the set of its vertices into two subsets which have no common edges at all. Let's say as you can see here, we can split the set of vertices into two subsets. This subset of vertices has no edges between them at all. So does this subset. This is another example of a bipartite graph. As you can see, we can split this subset of vertices into two this set of vertices into two subsets of vertices which are not connected between each other. I can draw this graph like this. One, two, three, 4, 5. 1, 2, 3, 4, 5. Now I will describe you the algorithm itself. I will describe you in this example. First of all, we have a bi-connected graph. And we want to check if this graph is a planar one or not. The first thing we need to do is to find any cycle in this graph. Let's take this cycle. 1, 2, 3, 6, 7, 8. I will draw it here. And now I'm gonna draw the rest of the graph. 2, 8. Sorry. 2, 8. 1, 7. And this subgraph. As you can see, we have path 1, 2, 3, 6, 7, 8, 1, and we have 3 other subgraphs. 1, 7, 2, 8, and a graph, and as a graph that contains the 4 vertices, 3, 4, 5, 6. But as you can see, now it's not obvious if it is a planar graph or not, because we have at least 2 intersections. So I will draw these 3 subgraphs separately. 1, 2, 1, 7, sorry. 2, 8, and this subgraph. Three, 4, 5, 6. Let's say this is a subgraph A, this is B, and this is C. And now we need to create a new bipartite graph which contains A, B, and C as its vertices. A, B, and C. As you can see, this circle 1, 2, 3, 6, 7, 8 splits all the surface into 2 pieces, outer piece and inner piece. And there is a Jordan curve. Jordan curve theorem that states that if we have a circle on a surface, this circle splits the surface into two pieces, and if we choose one piece, one point in inner subsurface and the other point in another subsurface, we will not be able to connect these two points with a path which doesn't intersect our initial circle. For us, it means that a subgraph 1, 7 and 2, 8, we will not be able to draw two subgraphs 1, 7 and 2, 8 in one sub area, subsurface. It means, so if we are not able to draw these subgraphs into one area, sub-area, we state that this new bipartite graph, which we want to be a bipartite graph, has this edge. This means that A and B have to be drawn in different subsurfaces. As you can see, the C subgraph can either be drawn in this subsurface or this inner subsurface. So, and now we have a graph ABC, which contains vertices A, B, and C, and which contains only one edge, A and B. And now we just need to detect if this graph is bipartite. It's obvious that it is, because we can split this graph into two, the set of its vertices into two subsets. Let's say this and this. After that, so now we can draw this graph like this. As you can see, in this part of graph, we have no intersections anymore. But now we need to check if this graph, this subgraph 3, 4, 5, 6 is a planar one. In this graph, we do the same thing. We can find any circle. Let's say this. Three, 4, 5, and 6. And we have two subgraphs 3, 5 and 4, 6. Let's say 3, 5 is D, and 4, 6 is E. These two subgraphs cannot be drawn in one sub-area, so if we want to draw this graph so that it will not have any intersections, we have to draw D and E in different subsurfaces. This means that our new graph looks like this. Is it a bipartite graph? Of course it is, because we can split the set which contains only two vertices into two subsets, this and this. And now our graph will look like this. As you can see, this graph is a planar one. Now I redraw this graph so that its edges will not have any intersections. Now, as you can see, this graph is a planar one. Let's check if this graph is a planar one or not. This graph called K33. And it is also a bipartite graph, as you can see, because we can split the set of its vertices into two subsets, which have no common edges at all. Okay. Let's choose any circle in this graph. We can choose 1, 4, 2, 6, 3, 5, 1. One, 5, 3, 6, 2, 4, 1. And it also has a few subgraphs, which is 1, 6, 2, 5, and 3, 4. Let's say this is subgraph A, B, and C. As you can see, we cannot, now we want to build this graph, a graph of graphs, and to check if it is a bipartite one. First of all, as you can see, we cannot draw subgraphs A and B in one subsurface. 1, 6, 2, 5, because it will have, this drawing will have intersections. We cannot draw subgraphs B and C in one surface, because they will have intersection as well. And we cannot draw subgraphs A and C in one subsurface. So we have a new graph of subgraphs. Let me draw it to you like this. A, B, C. And now we want to check if this graph is a bipartite graph. As you can see, it's not, because we cannot split the set, which is A, B, C, into two subsets, so that these subsets have no common edges at all. So it means that this is not a bipartite graph, and it means that this graph is not a planar one. But now we have a question. What if our graph is not a biconnected graph? Let's say we have connected graph, which is not biconnected. What does it mean? It means that this graph has a few means that this graph has at least a few vertices which we can remove, and this graph will not be connected anymore. But if we want to check planarity of this graph, we just need to check the planarity of these subgraphs. This subgraph, this subgraph, this subgraph, and this subgraph. As you can see, as you maybe see, these four subgraphs are all biconnected. And we can use our algorithm to check the planarity of these subgraphs. Okay, let's say we have a non-connected graph. This is the example of non-connected graph. To check the planarity of this graph, we just need to split this graph into two connected subgraphs and check the planarity of each subgraph separately. So this algorithm allows us to check the planarity of any graph. Let's make a quick overview of this algorithm. First thing we need to do to find any cycle in this graph. Second, we have to check. We have to create a graph of graphs and check if it is a bipartite. And the third thing we need to do is to check recursively if all the subgraphs A, B, C, and so on are planar. That's it. Now I would like to tell you about pros and cons of this algorithm. Pros. Of course, one of the of the most important pros of this algorithm that it is very easy to describe and to understand. So if you are not very familiar with graphs and planar graphs, if you are not familiar with graph theory at all, it would be easy for you to implement this algorithm and to check if a graph is planar or not. And as I mentioned, the second important pro is that this algorithm is very easy to implement. What about the cons? Of course, the main con of this algorithm is its complexity. The complexity of this algorithm is O(n power 3). Of course, this is not the best algorithm to check the planarity of a graph, but this algorithm, as I mentioned before, is very easy to understand and to implement. Thank you for watching.